So in question 1, it's a show that. We have to show that the area of this compound shape consisting of two trapezia is the expression given here. Please pause the video and try this. Okay, let's have a look at the full solution. We are asked to calculate the area of this compound shape, and you may have noticed already that this compound shape consists of two trapezia. What I'm going to do first is to distinguish between the two trapezia by labelling them. The first trapezia, we're going to call this one 1. I hope that makes sense. Got 1 here, so number 1. And this one we're going to refer to as number 2. And then to get the area of the compound shape, we can add the areas of 1 and 2 together later. I'm going to use the formula for the area of a trapezium that you met at GCSE. I won't be dividing each trapezium into a triangle and a rectangle because that won't serve our purpose in the lesson on the trapezium rule. I will use the formula. Let's write down the formula for the area of a trapezium. So if you'll remember from GCSE, the area is equal to 1/2 multiplied by h multiplied by a plus b. And just to be clear about what the h and the a and the b represent, the h we've got here, this is the height of the trapezium, which is the perpendicular distance between the two parallel sides. I'll just indicate this on here because it is important. So each trapezium has a pair of parallel sides. In fact, the definition of the shape is that a trapezium is a four-sided shape which has one pair of parallel sides only. So the A and the B represent each parallel side. You add those together, you multiply the sum by the perpendicular distance between the two parallel sides, and then you divide your answer by 2. So let's have a look at 1. So for trapezium 1, let's write this down. So the area of 1 is going to equal 1/2. Now the h is the same for both of these, so it's just h. And then the two parallel sides are y0, y0 indeed, and y1. So we'll add those two together, like that. And we can leave it like that if you like. And now for the area of 2, it's exactly the same principle. These two sides, y1 and y2, which I'll just indicate here, are the parallel sides. We add those together and multiply them by h and then divide by 2. Let's write that down. So the area of 2 is going to equal 1/2 of h again, and this time we're adding y1 and y2. Like so. Great. Now we're asked to find the area in a particular form. I've clearly got to add these two areas together. So let's make that distinction. So the total area and the question tells us this is called A. So I've got a name for it. Total area is A. Must equal 1/2 of h multiplying y0 plus y1, and then I add 1/2 of h, and then y1 plus y2. Like so. Next, we're going to expand this, because it's clearly not in the form we want. We must have to do some sort of manipulation. So this is equal to 1/2 of h y0 plus 1/2 of h y1 plus, and this is expanding the second bracket, of course, 1/2 of h y1 again plus 1/2 of h y2. You'll be able to see now that if we collect like terms, we have two terms containing y1. We've got, or if you like, we've got 1/2 lot of hy1 and another half lot of hy1. We can add these two together here, and that will give us 1hy1. But we need to factor out a half h. So what I need to do is, if I factor out the half h, so this is the final part, I only have one y0 term, okay, and I'm factoring out the half h, so that's just going to give me y0. Now, here I have two lots of a half h y1, and I'm factoring out the half, so I must have two lots of y1. Okay, if you're not convinced, just multiply that out and you'll see it works perfectly. And then I take the half h out of this, so I'm left with y2. And the principle we're going to come back to in the trapezium rule lesson is the fact that we have two lots of the y1 in the middle. This side has been used twice when calculating the area of the compound shape. Next, we're asked to integrate cot x with respect to x, and more specifically to use the substitution cos x over sin x. Please pause the video and try it. Okay, let's have a look at the full solution. Let's write in the substitution for the integrand. So this is equal to the integral, and I'll do it in red just to really emphasize this. So it's the integral of cos x over sin x. Remember, of course, tan x is sine over cos. And this is all with respect to x, so that's dx, like so. We have a fraction, and remember, when you're integrating fractions, there are a series of questions to ask yourself. The first question is the numerator the derivative of the denominator? The answer is, of course, yes, because the derivative of sine is, of course, cos. This means I can write down the answer, so you don't need a lot of space here. This is a log function. So in conclusion, I can write down the answer. You've done this a few times now, so it's the natural log of the modulus of sine x and plus c. There we go. Next, we're going to apply the previous result in question 2a to evaluate cot x integrated between pi over 6 and pi over 3. Please pause the video and have a go. Okay, and let's have a look at the solution. In typical fashion, we are now asked to integrate a definite integral from pi over 6 to pi over 3. We have the antiderivative already, and obviously we're going to use the previous result. It says hence here. I've written out the question just to really emphasize this. That is really important. If it says hence, then yes, follow the instructions. Don't start from scratch and do something else. It's completely unnecessary. So hence, yes, we are going to follow through with this. Antiderivative time, so we can rewrite this with limits on the right hand side. Let's do that over here. So this is equal to, big square brackets, the natural log of the modulus of sine x, like so. Close the modulus, of course, and evaluate it between. So pi over 3 will be my upper limit. I'll do that in red. And pi over 6 is my lower limit. I will do that in green, which you can see, obviously. Pi over 6. And let's substitute in these values. So now we can take our curved brackets. Now we replace the square brackets with curved brackets and take the difference between the limits substituted in. So this is equal to, open your curved bracket, and natural log of sine of pi over 3. Okay, so sine of pi over 3, put that in. Close your modulus. This is a positive value, of course. I mean, there's nothing to worry about here. This is not going to be negative, but we'll leave the modulus sign in as a precaution. Close the upper limit, and we're now going to subtract the lower limit. So this is the natural log of the modulus of sine of pi over 6 now. And we close the modulus. Again, this is positive, but we'll put it in there. I don't want to do too much in one step. To evaluate these sine values, we can use our calculator, but I'm going to just emphasize the fact that we can use a right angle triangle as well. These are key angles that you need to know. I'll just reinforce this. So if you draw a right angle triangle, like I've done here, like so, let's get rid of that bit. You have two angles, pi over 3 and pi over 6. If you don't like dealing with radians, of course, remember pi over 3 is simply 60 degrees and pi over 6 is 30. If I label them, I'll do these in blue. So the smaller angle will be pi over 6. So I've not drawn this terribly accurately, but it doesn't really matter. So pi over 6 and pi over 3. And then the thing to remember is, because this is the larger angle, this opposite side is going to be larger than this opposite side. So I'm going to go 1, 2, and root 3, which is how to remember it. So we can see clearly now that the sine of pi over 3 is going to be opposite over hypotenuse, so that's going to be root 3 over 2, and the sine of pi over 6 is going to be opposite over hypotenuse 1/2. So nice little tool there. Let's continue with the question. So this is going to equal the natural log, and we just evaluated the sine of pi over 3, so that's going to be root 3 over 2, like so. Subtract the natural log of pi over 6, which is simply 1/2. Okay, and there's many different directions we can go here. I'm going to use the subtraction law for logs, which is also the division law, however you want to interpret it. So I can write this as a single logarithm straight away. And I didn't specify how to write this answer when I set it. It's up to you really. I think the idea is just to make the answer look as simple and elegant as possible, but still exact. So we're going to have the natural log of root 3 over 2, like that, all over 1/2. With the log taken. I can simplify this. If I want to simplify my fraction, I just multiply the denominator and the numerator by 2. I'll do that just to add a bit of working in there. So we don't like fractions inside fractions. If there's a way to clear them, then we'll do it. So if I multiply this by 2 and I multiply the numerator by 2 also, I get √3/1. So my final answer, which I'll just write on the right hand side here, is just going to be the natural log of the square root of 3. Very nice indeed. Here we're going to use some of the reasoning that we saw in the previous lesson. So we are interested in the area enclosed by two functions, f and g, and the line x equals pi/4. So please pause the video and try this question. Okay, and let's have a look at the solution. In question 3, we're given quite a lot of information, so I've included a diagram here, bit of hair on there, and what I've done is I've shaded in the area bounded that we need to find. And you'll notice we can probably use, or in fact we definitely can use, the principles that we met in the previous lesson on finding areas, because the area that I'm interested in is the difference between the integral of y equals f of x from 0 to pi/4 and y equals g of x integrated between 0 and pi/4. So I'm going to write that as a single integral, and you'll see what I mean in a second. So this area is represented, or can be represented, as follows. So the integral from 0 to pi/4 of f of x subtract g of x dx. Alright, and that is one single integral. I will put brackets around this to be correct, well, more than anything. So there's our integrand. I'm going to now substitute in our functions. So the functions we're given are that f of x is tan squared plus 1 and g of x is the function 1. So let's write those in. So this is equal to the integral from 0 to pi/4 of tan squared x plus 1, so that's my f, subtract 1, and that's with respect to x, of course, dx. And we'll make the distinction in a second. So this is my integrand, and my f function is here. So this is the tan squared x plus 1, which represents f, and the 1 represents g. Notice that the plus 1 and the negative 1 will cancel. So this is going to leave me with a more straightforward integral, but there's more work to do. So this is the integral from 0 to pi/4 of tan squared x dx. Okay. We're then told that we can use a substitution, or an identity. So the identity is that sec squared x is 1 plus tan squared. If I just rearrange the identity for a second, I'll do this over here on the left. So sec squared is identical to 1 plus tan squared x. Okay, simple rearrangement. That means that if I do sec squared x subtract 1, I've got my tan squared x. that means I can now make a direct substitution in my integrand. So this is going to replace the tan squared. Let's do that. Now I've got a bit more room over here. I'm going to put my next step on the right hand side here. So this is going to equal the integral from 0 to pi over 4 of sec squared x subtract 1. It's a bit of a trick, really. I included the subtract 1, or the plus 1 I should say, in the f of x, because you can get carried away and just want to substitute all of this with sec squared. So do be rigorous with this and take your time. Okay, and that's with respect to x, of course. So there's a dx on there. Just fit that on. Okay, and we'll put the brackets around that. So now we're ready to integrate. So if you remember, sec squared is a standard integral, and 1 is also a standard integral. It's very straightforward from last year. So I'm going to drag my equal sign across, and so going all the way down here. So this is going to equal the integral from 0 to pi over 4 of sec squared x dx, subtract the integral from 0 to pi over 4 of 1, or just dx. If you like, I'll put the 1 in there just so you're clear. So that's 1. So again, I've used the principle from the previous lesson where I can separate my difference between two functions as two separate integrals. Let's apply the standard results now. So not much more to do now. So this is going to equal tan x evaluated between 0 and pi over 4, standard result, and subtract x also evaluated between 0 and pi over 4. You didn't have to do it that way, of course. You could have just kept the integrand as it was and integrated term by term, but I thought I might as well use that principle again. And we're ready to write down the answer now. I'm not going to use the curly brackets because this is pretty easy. If I do tan of pi over 4, that's simply 1. Tan of 0 is 0. So this is going to leave me with 1 for my first upper limit evaluated. And then for my lower limit, I'm going to be subtracting the difference of pi over 4 and 0, which is just pi over 4. If you want to put an extra step in, you can, but you don't need to here. So subtract pi over 4. And if you're interested, that is approximately, so just put roughly 0.215 evaluated to 3 significant figures. There we go. And the last question, we have a definite integral where we have to use a little bit of reasoning, quite similar to an exam question. Please pause the video and try it. Okay, and let's have a look at the solution. Lastly, we have a rather nice question which will allow you to showcase a lot of your skills. This is the kind of question you might see in the published examination material. Now, what we have here is a definite integral where we don't actually know what the limits are. They're given in terms of k, and we are in fact given the evaluation, what the value actually is. Let's get straight to it. Now, we have a fraction that we're going to integrate, so you have to ask yourself those key questions. Is the numerator the derivative of the denominator? Well, the answer is of course no, but can I perhaps do some manipulation to force the numerator to actually be the derivative of the denominator? Now this is where we can use some of our skills. The derivative of the denominator is of course 2. Now, how can I make the numerator 2? Well, let's remove what I've got so far. So it's 1 at the moment. I'm just going to remove that. And 2 is what I want, because if it was 2, I can use the log function. So I'm going to put 2 in here, like so. But that's cheating, isn't it? Because I've just changed the question. So what could I do to make up for changing the numerator? Well, if I multiply my integral by 1/2, it will cancel out the 2 and I won't have changed the question. So let's put 1/2 on the outside. So 1/2 will go here. Great, now we can go straight to the integration. We have to remember, of course, that we're multiplying the entire thing by 1/2, so I'm going to be using square brackets through most of this. So we're going to have 1/2, and we integrate this, so that's going to be the natural log of 2x plus 1, inside the modulus, of course. We'll close our square brackets, and the limits are, of course, k and 2k. So we'll put those in. And this is all equal to the natural log of the square root of 3/2. Now, rather than using the square root, because we're dealing with logs, which consequently means we're going to be dealing with indices, I'm going to write the square root as a power 1/2. So this is going to be the natural log of 3/2 to the power 1/2, like that. Great. Now what can we do next? Well, we can substitute in our limits, and there may be some log laws we can use shortly. So this is all going to be 1/2, and then I'm going to use the curly brackets, of course, but I'm going to keep the square brackets on the outside. So we've got 1/2, square bracket, now curly bracket, now the natural log, and I'll take the modulus, but I'm going to substitute in my upper limit. So it's 2 lots of 2k, so that's going to be 4k plus 1, and then I'm going to subtract the natural log, and that's going to be 2k plus 1. Close that. And to be honest, I didn't actually need the curly brackets, did I? But never mind. And that's going to equal, now if you look on the right hand side, I can do a bit more work here. I can bring the half down to the front because that's the power law. So this is going to be 1/2 of the natural log of 3/2. Now this is interesting. We have a half multiplying both sides of the equation. That means I can just simply remove them. I can divide both sides by a half and pretend they're not there. So let's do that. So I'm going to remove the half here and the half there. So it makes it a little bit more simple, doesn't it? Great. What next? Well, I've got a log subtracting a log here. That means I can hopefully use the division law or the subtraction law, however you want to call it. So if I write this as a fraction, so this is going to be the natural log of 4k plus 1 over 2k plus 1, which is equal to the natural log of 3/2. Fantastic. Right, we can now remove the logarithms, because we're taking the log of both sides. We are taking the log function of both sides. We essentially raise both sides by the power e, which just cancels out what the log is doing. So we have an equation we can solve. So the equation we're going to solve is this. We're going to solve 4k plus 1 over 2k plus 1 is equal to 3 over 2. Okay, let's use implication. Well, how can we do this? Let's rearrange it. Let's get rid of the fractions. So we're going to have 2 lots of 4k plus 1 equal to 3 lots of 2k plus 1 also. Right. Expand, simplify, collect like terms and solve essentially. So 2 lots of 4k, so we have 8k plus 2 is equal to 6k plus 3. And I won't do many more steps, but this implies subtract the 6k from both sides and subtract 2 from both sides. So I'm going to have 2k equal to 1. Fabulous. So k is a half. There we have it.